This is my one of my project in which I try to detect faces in an image so as to separate an image with faces and without faces. So to start with, like these are some important imports that we need to do. I've already run that project, so I'll not run it again. I'll share the link of the file. You can always run it. So next I'm making use of the GPUs, the Google Colab provide. So in the runtime, you can change this runtime and select GPU and then save, and then click on save. So we were just checking like number of GPU devices and which particular GPU was allocated to us. So it was Tesla T4, which is considered to be a very good GPU. So we'll have like faster computing speed basically. Now coming on to the data set, I have created a custom data set for this using two different data set, both from the Kaggle. One is Cipher 100 and the other is a different data set which have roughly 70,000 images of faces. Why I created a custom dataset? Because in Cipher 100, I have only like one superclass which contains five subclasses. So, which have humans in it, like baby girl, baby boy, then a man, woman, and like the classes like these. So it created a problem of unbalanced data set. So to overcome that, I removed uh, all the images of people superclass, and which makes it roughly what 4700 550 images. So I went to the different data set with all the human images. I took exactly these numbers of images and do all the necessary changes to the image, like I have to convert it first from RGB to grayscale, then I have to resize it to 32 by 32, and then I have to flatten the image as well. I flatten it so that I can stack it in the data frame of the existing data that I already have from the cipher, and then I randomly shuffle the data so that we can get a good balance while splitting the data into training, validation, and test data set. So I use a different like I did that in a different project. So I created a CSV file which I uploaded here. So yes, so for uploading the CSV file, I created a directory. Then I moved that to the desired directory so that I can I can download the CSV file into this directory. Then I was trying to access the like because I uploaded the CSV file to the Google Drive. It was giving me some error, access denied. So this was one workaround of that. This is the link basically of the CSV file. So here I'm downloading that CSV file. So then further I'm just this is where I read the CSV file. Then I'm converting all the values from float to int, and this is where I'm do the data shuffling that I was talking about. There were few redundant data in the beginning, so I removed those two columns, and this is our clean data set that we required, because 32 by 32 image, flatten it will make it 1024. So this Y is our label column, like whether this image is of a human or not. So 0 is not a human, 1 is human. So yes, this is the shape of the data set. This is columns. Okay. Then I use a train test split from Scotland library, and so that I can make a good split of training and test database. I took a split of 25%. So 75% is my training database, 25% is my test database. Keep the random state one so that I can, you can say replicate the same split every time, so that you guys can have a similar, you can say, accuracy score, as well as everything same like what I'm showing you in this video. So this is just visualizing the training data. This is the size, this is the shape basically, this is the data, this is the y value because I'm splitting the data into x and y values. Then this is the test data, again just simply visualizing and splitting the x and y values so that we can feed it to our accuracy score method and check the what's our accuracy. Then I make use of the feature scaling, although it doesn't require feature scaling because all the values are like roughly of the same range, because they belong, because these are all just pixel values, so they probably lie within the same range like 0 to 225. But I still did that so that we can have a faster computation. So, okay, this is just feature scaling of both the training data as well as the test data. So again, just visualizing, rechecking like everything is fine. Okay, shape is all fine, data is all fine. So it generates a value between a particular range. Then I'm creating, like I'm making use of the KerasTuner to build a model. I'm not using any, you can say, predefined model like YOLO and or the other, but just to to have a idea of how KerasTuner works. So I make use of that. So yes, I'm downloading basically KerasTuner here. Then I'm installing the KerasTuner to the desired directory. Then these are all the necessary imports. You might have some duplicate imports, but okay, it's fine as of now. Then this is the model that we're talking about, which our KerasTuner will run for different iterations to get the best model. So this is just a parameter for hyperparameters, because we'll be tuning those hyperparameters to create a different models on which KerasTuner will calculate our, you can say, accuracy, validation score, val score, like val loss and accuracy, to tell us like which is our best model. So yes, so we use this method so that range is typically used to to tell, like, to give a model range like between 2 to 20. You can have any number of values as you want. So this is just a model, like this is just a for loop. So then we add a dense layer in the beginning. For dense layer again, we are, like, for the number of units, we are giving the minimum value can be this, maximum value can be this, with a step size of this, like you increase the value with a step of 32. And this is just to give different, you can say, layers a different name so that you can see like which layers have how many units. And as directed, like as it's a standard norm, that hue uniform is considered to be the best kernel initializer for hidden layers. So is the ReLU as an activation for the function for the ReLU layers. We're not making use of the dropout as of now. So then finally, this is the output layer. So for output layer, Gloret uniform is considered to be the best, and for activation, because since it's just a binary classification between human and non-human, like 0 and 1, so sigmoid is considered to be the best for that. Then we are here we are compiling the model in which we are again giving the KerasTuner to choose between the learning rate. Like these are the three learning rate that we have. Yes, these are the three learning rate that we are providing to the KerasTuner so that he can choose. And then for compiling, this is because it's a binary classification problem, so it's a binary cross entropy is apt for it. Then matrix is accuracy, because we want our accuracy to be very good. Then so here we are now I have also, you can say, try to visualize these more different models through the tensor board. Although I'll not be going in detail to the tensor board, like visualizing and you can say going through in deep what the tensor flow is doing. But we can have a glimpse of it. So, okay, these are the Keras tuner. Basically, this is where we are telling our model, like, okay, uh, this is where we are telling the Keras tuner, like, how to go about, like, how to search for the best model. So, we are feeding him the model that he needs to search for, like, he need to run. Then the objective is our to have the minimum val loss, because these are standards parametrics. So tuners already know that, okay, for the minimum value I have to run our model. If you create a custom objective, you have to define that whether the tuner have to look for the minimum value or for the maximum value. Then these are the max trial, like how many trials the tuner has to run for, and these are the execution, like for each trial, how many executions KerasTuner has to perform. So, okay, then okay, this is the directory where we are storing all the results. Like, we'll be getting all the stats. So we are storing there, and this is the project name for that. So if you go to this directory with this project name, you can find all the logs. So we're just looking for the what's our tuner summary. So okay, then here we are searching for the best model, as I've already run it, because it takes a lot of time. It almost like 40 minutes. So to save our time, I pre-run it, and like it's showing the detail. Like for fifth trial, it's for 9 minutes. Val loss is this of the fifth trial. Best val loss is 0.28. The range maximum is 0 to, like, range is 0 to 1, so 0.28 is pretty good. So this is the tensor board that I was talking about. So you can see, like, so these are all the executions. Like I was telling you, like there are five trials. For each trial you have multiple executions. So these are, all those trials and execution. It's 0 0 0, then 1 1 1, then it's 2 2 2, and so on and so forth. So this is all the graph that it has drawn for the accuracy level. Then this is for the loss, like how as we progress, as our how we are progressing the model is getting fine tuned and the loss is getting minimized. This is for okay, accuracy. This is again val. This is for validation data. This is for the training data. Okay. So now we have trained our model. We have done everything. We have got numerous models. So now our task is to select the best model. So we pulled out the best two models using the get best models, and then the best performing model is at the top. So at the model at the zeroth, we took that best model, and then we uh, just telling the model that okay, this is our input is going to be like the shape of our input, then this is the model summary. So for the best model that we have built, this this is the exact model. You can see these are the number of layers, these are the number of units or neurons in each layer. Obviously this is the output layer. So now our model is built, everything is working fine. So now how to check that whether our model is working or not. So hmm, so yes. So here we are. In this, I'm just checking like how many. First of all, I'm predicting using the test data Y prediction, creating the Y prediction list. You can say. Uh, so here I'm doing that only. Then this is just checking like how many human images we have. So this is the Y prediction over the X test, and this is the number of humans. Um, if you notice, this is somewhat 50% of our test data. So it was just to double to get like really sure like it's working fine. So finally, I just fed that Y test and Y pred to the accuracy score model, and our accuracy score is come out to be 0.98, and the range is considered to be 0 to 1. This is, you can say, 98.91%, which is really good. So that's it. Thank you so much.